We've inspected them. Yeah, they were supposed to move and condense.
Did you want us to finish this?
We'll finish it next time. There we go. Okay, so what we're gonna do as soon as it comes back on is we're gonna talk about some analytic geometry done in the time period. What time period are we talking about, guys?
1600s.
Early 1600s. So analytic geometry, and the whole goal was to be able to draw a tangent line to a curve. So this is what you guys were reading about. Sweet. So yeah, drawing a tangent line to a curve. Now, we're going to use an example. We're going to use the curve y squared equals to 4x, which is a parabola that opens something like that. This is our x-axis, and so we're going to be at some point over here. And the book, I believe, calls this one x1, y1. And that's where we want to draw our tangent line. Now, what they knew in that time period, okay guys, sorry I can't draw. What they knew in that time period is that circles tell me about the relationship between that radius and that tangent to that circle. What does it look like? Perpendicular. The radius of a circle is perpendicular to the tangent line of the circle where they intersect. So the whole point was to construct some sort of circle through here with the center down here on your x-axis, and then you can write the equation for this line through those 2 points, and then you know what the slope is, and you can write down the equation for the perpendicular line. Well, the trick is you don't know where that intersects on the x-axis, where that center is supposed to be on the x-axis. So we have to give it a name. What is the y value on your x-axis? What is y equal to? Yeah. Say it again, Dalton. 0. Y value is equal to 0 on your x-axis. So you do know that one value right there. This is going to be x2, 0. What's the equation of a circle? Okay, so what is the h? The h and k are the center of your circle. So in my case, this is my center. So what do I have? I have x minus x2 squared plus y minus what's k? 0. Now, I know r is the distance between my 2 points. The one on the parabola and the center of the circle is going to be r, right? So what is our distance formula? Square root, change in x, right? x1 minus x2 squared plus change in y. y2 minus 0, right?
Yeah, it would be 0 minus.
Oh, it's a y1, sorry. y2 is 0. So you want it 0 minus y1, we can do that. Really doesn't matter which order I put it in. Yep. Now remember, it's r squared. So I ran out of room. We have to square it all. What happens when you square a square root? It goes away. So we have this equation, x minus x2 squared plus y squared is equal to x1 minus x2 squared plus y squared. Now, okay. No, that's a y1 squared, sorry. This is a y squared and that's a y1 squared. Now I can't quite cancel them. We can FOIL though, right? Uh-huh. So let me make sure I don't make any more mistakes here. FOIL it out. What do you get when you FOIL? Plus y squared. FOIL. Minus, yes. I'm testing myself. See if you guys are awake, right? Yeah, he already fessed up. Now, notice we have one other piece of information. We are on this curve right here. So y squared is going to be 4x. So that's what we're going to plug in down here. And let's see what that gives us. Do we have anything that cancels on both sides? Cly was mentioning something. X2 squared. I think that's it. Yeah. Let's go ahead and set the whole thing equal to 0 because our goal is to solve for x. So subtract everything over to the other side. So we get what? A minus x1 squared plus 2x x1 x x1 x2. Yeah. Minus y1 squared, right? Now, are there terms that we can factor out combined together? Well, we have an x2 on both of those, right? So we could take something out from there. And then we have a 4x. I'm missing something, guys. Oh.
It's supposed to be 16x squared.
They give us a point in the book.
Oh.
We have gone as far as we can without knowing what x1 and y1 are going to be. The point they give us in the book, if you look in the book, they give you 1, 2.
Oh, that helps a lot.
I was going to say, we're kind of done. This is a general equation, guys. Now you write a quadratic formula and you'll be done, right? Because you have power of x squared, and then you have constant terms right here, and you can have the x, this is part of our constant. You have just an x here. So it's a quadratic and x, and you could use your quadratic formula. But let's simplify it the rest of the way. It is 1, 2, so plug in 1 for x, 1. This is going to be our 1. So we have x squared minus 2x x2 plus 4x minus 1 squared plus 2 times 1 times x2 minus 2 squared. Now it gets prettier. Tell me what happens to the minus 1 when you square it. It's not a trick question. It's still a minus 1. It is not a trick question, guys. How about the 2 when you square it? 4. It just depends on what? How you write it?
How you look at it.
Oh.
Whether it's a trick question.
Oh, okay.
I said everything.
Everything is a trick question? Could possibly be. No, when I'm asking a question, it's usually my way of slowing me down so I can actually get to the right answer when I'm thinking about it. It works for me. Okay, so this minus 1 and that minus 4 are going to get you a what? Negative 5. So we're going to have an x squared minus a 2x x2 plus 4x plus 2x2 minus 5. These are constant terms. That's going to be c from our quadratic formula. I'm going to factor out the 2x from those two terms. So you have x squared minus 2x, and you're going to have x2 minus 2, right? Minus? Yeah. Plus 2x2 minus 5 is equal to 0. Quadratic formula. We are unsure if they actually knew the quadratic formula, but we're pretty sure they did. So A is 1.
Why do we leave the 2 out of our B?
Yeah.
Oh, it's part of the B.
I don't think
Part of the B.
that is not the X.
So what is our quadratic formula? X is equal to?
Plus or minus the square root of B squared
All right, guys. All over 2a. Perfect. So let's plug this in. Now, when you're trying to solve this for the quadratic formula, there's actually a shortcut that we can take because we're looking for one particular x value. We're not looking for two x values because we're trying to solve for just one x value solution for this, not a dual root. What is the way to only get one solution out of here? Yeah, this plus or minus part has to be 0. So one solution means we want b squared minus 4ac equals to 0. And that's what we're going to solve. B squared minus 4ac equals to 0. Now, b is going to be 2 times x2 minus 2 squared minus 4. A is 1, and c is 2x2 minus 5. Okay. We're done, right? Foil this. You're going to have 4x2 minus 2 squared. We'll get to foiling in a minute. Minus 8x2 plus 20. And then that becomes x2 squared minus 4x2 plus 4. Is it gone?
No, it's not gone. It'll just be -4.
So 4x2 squared.
Yeah.
back to 4 out.
What is, yeah, combine things. Was 16 and a 20? 36. X2 squared. Oh, minus 24. Yeah, there's two of those. X2 plus 36 equals to 0. Now someone said factor out that 4, so why not? What is 4 into 24? 6. So that means we're solving the equation x2 squared. So it's x2 minus 3 squared. X2 is equal. Now that's just the x2 value. So the center of our circle is going to be 3, 0. Now we found our center. Now let's go back up. I'll slide this down in a second. Go back up here. Remember, we're looking for the tangent line, so we have to find the slope between the 1, 2 and our point of 3, 0. How do you find that slope? Rise over run. So 2 minus 0 over 1 minus 3. Yeah, so what's the slope for the perpendicular to that? 1. We chose our numbers nicely, didn't we? Very nicely. So what would be the equation for that line then? Well, except there's a shift in it because it has to go through 1, 2. So it's y minus 2 is equal to 1, x minus 1, or y is equal to x minus 1 plus 2. There's our equation for our line. Yeah. Makes you appreciate calculus, doesn't it? All you have to, all you have to do in calculus is take a derivative to find the slope. Yeah.
This is before calculus, right?
This, yeah, 1600s, right? So, and calculus doesn't come along until,
Later on.
yeah, good call, guys. Isaac Newton, yeah, Leibniz Newton. You're talking about 1700s to early 1800s. It's calculus. So there is all of that work. That's on one page.
Wow.
Okay, and one other,
Calculus made it so much more simple.
yeah. This is called analytic geometry. You're using geometry to solve the problem instead of using calculus for it. Okay, one other problem we wanted to look at, and then we're going to talk with our high school students. This one is like a homework problem. Okay, we already talked about showing that square root of 2 is irrational already. How did we do that?
Contradiction, saying it's rational.
Yeah,
Are we gonna do it the geometrically?
But in this, they.
Infinite descent. Yeah.
So, infinite descent.
yeah.
Oh.
I suppose I on infinite's capitalized when you're naming the method. So method of infinite descent here, show that the square root of 2 is irrational. Yours is actually show that the square root of 3 is irrational. So you're mimicking this proof in your homework, but it's not the exact same numbers. We're going to be assuming that it's rational, so it's still a proof by contradiction. What's the definition of rational? Yeah. And so, yeah, there exists, the book calls them A and B. Let me use A and B so follow the book. And then what are the natural numbers, guys? 1, 2, 3 counting integers, positive counting integers. Such that you're going to have square root of 2 is equal to A over B. Notice in this one, I'm not going to make any restrictions about the relationship between A and B. We don't have to divide out any common divisors. We're just writing them square root of 2 is equal to A over B. Now, I need some scratch work over here. Notice that if I multiply square root of 2 plus 1 and square root of 2 minus 1, what is, if I FOIL this, square root of 2 times square root of 2 is what? 2, or the square root of 4. And then you're going to have minus square root of 2 plus square root of 2 minus 1. What is? Yeah.
Wow.
So I'm going to use that relationship. I'm actually going to solve for the square root of 2 plus 1. This is going to be 1 over the square root of 2 minus 1. Make sure you actually do this scratch work for your proof, because square root of 3 minus 1 doesn't solve the same way. You're not going to have the same answer. You're going to get a different value. So make sure you calculate it. Okay? That's what I see. That's the error I see. Now, square root of 2 is A plus B. So we're going to plug in for A plus B right there. Sorry, A plus B, A over B.
Oh, okay.
Now, this is called arithmetic. What do you do when you're adding a fraction and a number? Common denominator. So let's get our common denominator. What do you think it should be? Yeah, a over b minus b over b. So then that becomes 1 over a minus b over b. What do you do when you're dividing by a fraction? Flip it. So we're going to have 1 times b over a minus b, which is just our b over a minus b. So putting that together, I have square root of 2 plus 1 is equal to b over a minus b. Solve that for square root of 2. It's going to be b over a minus b minus 1. What should we do with that minus 1? Get a common denominator. So I have minus and a minus b. So it's b minus a plus b. So that's going to be equal to, I guess I'll put it right here, 2b minus a over a minus b. That's what our square root of 2 is equal to. It still looks like a fraction, but these numbers look different. I am going to call this an a1 over a b1, and we're going to say where a1 is equal to 2b minus a, and b1 is equal to a minus b. We're not too concerned about the b1. We're most concerned about the a1. What we want to know is if a1 is bigger than, equal to, or smaller than a. What's the relationship? What does it look like to you? Do you think that a1 is equal to a? Do you think 2b minus a is going to be equal to a? Probably not. You think it's less than a? Yeah, that's what I'm thinking. So let's see if we can show that it's less than a. What do we know about square root of 2? Well, we know that, but what value? If you were computing the square root of 2, it's approximately equal to what? 1.4414-ish. So I know it's bigger than 1, right? And it's smaller than 2. So substitute a over b in. You're going to have 1 is less than a over b is less than 2. Multiply by your b, you have b is less than a is less than 2b. a1 is 2b minus a. This value right there. a1 is 2b minus a. So what should we have? What should we do? Subtract a. So we're going to have b minus a is less than 0 is less than 2b minus a. So I know that 2b minus a is bigger than 0. So it's a positive value. That's the first concern. The second one is it is smaller than a. I know b was less than a. That's what we have up there. So tell me about 2b and 2a. Yeah, 2b is going to be less than 2a, correct? Subtract a from both sides. What is 2a minus a? A. So that tells you that our a1 is less than a. Combining it together, I know that 0 is less than a1 is less than a. I got off on my lines. I need lined paper. So we're going to go down here. And square root of 2 is equal to a1 over b1. Now, help me out. Other than the convention that we've labeled it, a1 over b1, what is the difference between our a over b and a1 over b1? They look the same, right? They're natural numbers. Yeah, and a1 is smaller than a, right? So I have back to where I started with a smaller value for a1. I can repeat this same process using this a1 and b1, correct? Yep. How many times can I repeat this process based off of just the fact that square root of 2 equals a1 over b1? Infinitely many times. Yeah, we can repeat this infinitely often. How do you spell infinitely?
Like infinite.
Is that an I? There we go. Infinitely often. To get an infinite set of positive integers between 0 and a. Now, how many positive integers are smaller than a and bigger than 0? No, I'm talking real life now, not according to what I just wrote on the slide. Let's suppose a is 100 million. Yeah. There's a minus 1 positive integers between 0 and a, right? Not infinite. Do you see the contradiction? Yeah. So we have to fix what we broke. Square root of 2 is irrational. Little box at the end of that. That proof method came about here in the 1600s.
How about the one by contradiction? When did that?
That one is in the Greeks.
Oh, okay.
Euclid. That one was found in Euclid's Elements.
Okay.
And remember that was the Bridge of Fools because it looked like a bridge. No, that was the other one. No, that square root of 2 was from the Greeks, but it wasn't the Bridge of Fools, but yeah.
Okay.
Yeah. Okay, rest of this time period, you guys, seniors, are going to ask the rest of the class any questions you might want to know about classes at Southern or anything like that. And I think you guys ought to introduce yourselves to each other too. So start over here with Dustin and tell him who you guys are. And
I'm Dustin. I'm a senior. I am a mathematics major with an emphasis in secondary education.